All right, so we are now in our second set of notes for the kinetics part of this unit. So we are now at the top of page number 138. You're also going to need your reference tables. You're going to need to be able to look at reference table I because we're going to use that reference table. I am going to switch to my tablet mode. And then I'm going to get started on potential energy diagrams, which is a very important part of this unit, is understanding these diagrams. So from our last set of notes, we have two different shapes of these diagrams, or this graphical representation of what happens in a chemical reaction. So we have an endothermic and an exothermic shape of graph. So we have our exothermic graph over here, right? So an exothermic is a release of energy, right? So we have here, this is a potential energy diagram, right? So we have potential energy on the y-axis, and then this is just reaction progressing. And here we have potential energy on the y-axis. And so this is our endothermic. Right. So remember, we have endothermic and exothermic way back from the beginning of the year. Exothermic means releases heat. Endothermic means it absorbs heat. So if we can see that where there's a release of heat, right, because heat's a form of energy, right, we're having a conversion of energy. So then it's a release of energy because our energy is ending up lower over here. And then endothermic is an absorption of energy because we end up at a higher energy state. And so endothermic and exothermic have to do with what's called delta H, which is the heat of reaction, right? It means change in heat. And then we have a new vocabulary word. So this is enthalpy, right? Which is the change in heat. And how we calculate this is we take the potential energy of the products, which is this amount of energy here. This is the potential energy of the products from, let me get my little eraser because I went a little bit too far. So then this is the amount of energy that the products have stored. This is the amount of energy that the reactants have stored. Remember, because we start with reactants and we end with products. So the difference between those two is the delta H. And so how I like to find the delta H is I take my two flat lines and I extend it, and then any arrow in this region is the delta H. And so this is how much energy that the reactants have stored. This is how much energy that the products have stored. And then the delta H, or the heat of this reaction, is the difference, right? The difference means subtract between the two. So then I extend my two flat lines, and then any arrow in this region is the delta H, the heat of reaction. So the heat of reaction, by definition, or enthalpy, is the potential energy of the products minus the potential energy of the reactants. Whenever you have to take the difference between two things in science, it's always going to be final minus initial, where you end minus where you start. And table I has these delta H values at 101.3 kilopascals and 298 Kelvin. So let's go over to table I. So at 101.3 kilopascals and 298 Kelvin, these are the heats of reactions for a large set of chemical reactions. And also we have dissolving in water over here down at the bottom. And always we're going to read the fine print. And down here at the bottom, the delta H values, a minus sign indicates an exothermic reaction. Reactions that release energy are exothermic. The delta H is negative, heat's going out. Some of this is a review from way back when we did chemical reactions. And so if you have the energy on the right side, which is the product side, that means that energy is being produced and it's exothermic. So table I, exothermic, has the negative values indicating the direction of heat, not a number less than 0. Reactions that absorb energy are called endothermic because endo means in, exo means out. And the delta H is positive, heat's being added, and we have energy absorbed on the left of the arrow in our equation. And then this is the reactant side. And remember, we have two shapes of graphs. This is our endothermic graph because we end up higher. Oops. We have our potential energy, right? Because this is potential energy. We end up at a higher energy state. So energy had to be absorbed. In our exothermic shaped graph, which is right over here, right? Potential energy is on the y-axis. So when we end at a lower energy state, that means energy must be released. And then your delta H is in this space between these two flat lines, in between your reactant line and in between your product line. That's where you're going to find your delta H. So whenever you do a chemical reaction, right, whatever you do, if you reverse a chemical reaction, you reverse the delta H. So keep in mind when we did our types of reactions, we had synthesis and decomposition, and they are reverses of each other. So if I reverse a reaction, if I read it in reverse, because I can read from left to right and right to left, then I'm going to reverse the sign of the delta H. If it's endothermic in one direction, it's exothermic in the other direction. If I double the equation, then it means I'm going to double the delta H. So if I burn, let's say, 2 moles of octane and I release that large amount of energy, if I burn 4 moles of octane, I'm going to produce double the amount that I did when I burned 2 moles of octane. I'm always drawing these lines, right? Because you think I'd be able to, by now, you'd think I'd be able to get this whole, computer thing down. All right, so let's take a look at table I. Okay, so in our first example, I have nitrogen plus 2 oxygens making 2 nitrogen dioxides. So if according to table I, this is my delta H, and if you want me to see, so N2O2 to NO2, so N2O2 to NO2, and N2O2 to 2NO2. That's this one. Remember, you have to read this really carefully. It's not the one above because that's NO, not NO2. So that's a positive 66.4. So that's where that positive 66.4 comes from. So that's endothermic as a positive delta H. So if I take the next one and I look at this one on table I, this is exactly as it's written on table I. Okay, so negative 91.8, so it's exothermic. So now if I take this one, if I see this is NH3, this is the reverse of this one. So if it was exothermic from this direction, the reverse reaction is endothermic, but the quantity of heat is the same, right? Because we cannot create or destroy energy. So that's why this is a positive 91.8. So if I take a look at this reaction, this is a double of what I can see on table I, right? So if I have 2 moles of carbon plus 2 moles of oxygen make 2 moles of carbon dioxide. So now this is 2 moles, 2 moles, 2 moles. So this is double of what I see on table I. So I double the heat. It's still exothermic, but now I release twice the amount of heat. So whatever 2 times 393.5 is would be your answer. And this number 5 is the reverse of what you can see on table I, and also where the coefficients are cut in half. All right. So in a chemical reaction, we can read it from left to right and right to left. If we're reading something from left to right, the normal way that, we in the United States that we read, we call that the forward reaction. And so that's where our reactants are making products. We call this forward. Now, if I read it reverse, if I go this way, I call that the reverse reaction. So C plus D makes B and A instead of A plus B makes C and D, right? So we can read reactions forward and reverse. And since we can read reactions forward and reverse, we can read these diagrams forward and reverse. And now we're going to add something new to our diagram. So I know this one looks a little bit busy right now because there's already a lot of writing on it. So I'm just going to sketch a new one. So I'm going to sketch a new exothermic reaction like this. Okay, so here's my new exothermic chemical reaction. So the things that we've already learned so far, right? Because this is potential energy. And this amount of energy here under the curve is going to be our potential energy of our reactants. So I'm just going to do PE of R. And then this is my potential energy of my products, of my products. I'm going to switch colors and I'm going to use some orange. So now we've also learned about the heat of reaction, which is the difference between the potential energy of the products minus the potential energy of our reactants. So then to find out where that arrow would be, the amount of energy, I'm going to extend my two flat lines, my reactant and product line. And then here is now my delta H. There's my heat of reaction. This is exothermic. I know that because I end up at a lower energy state, so the energy must have been released. And my delta H is negative because I have the product, which is this lower number, minus a higher number will give you this negative number or heat going out. So now we're going to add to our graph. We're going to now talk about what is activation energy, right? So I've got this word active. If I'm going to activate something, it means I'm starting it. If I activate, my video game console, right, it means I'm starting it up. So that's what it means in a chemical reaction. The activation energy is the energy needed to get a reaction started. But you have to add a little bit of energy. Even if something is considered a spontaneous reaction, there has to be some sort of energy transition. And so at the very, very top of this line, we have what's called the activated complex, which is a temporary energy rearrangement of the reactants before it has started to make products. So in order to get this reaction, this is where the reaction is starting, right? We form this activated complex. In order to do that, let's switch colors. What's a good color for activate? Green, right? Because green means go. All right, so I'm going to do this. So from my reactant line to the top of the hill, to the activated complex, right? Up to the top of the hill. This is what's called the activation energy. So I'm just going to do that. That's the activation energy in the forward direction, right? If I'm going from left to right. So if I'm going in the reverse direction, now I just have to read this in reverse. This is my activation energy going into reverse. So activation energy is called EA, energy of activation. So there's two different activation energies. Notice it takes much more energy to go in reverse in this reaction than it does to go forward. That makes sense. All right, so that's our activation energy. And so this has two different lines in this graph right here. So in living environment, you learned that an enzyme is a catalyst. So what is a catalyst? So I'm going to just switch to yellow because I think yellow is a good color for a catalyst. So a catalyst is going to shorten the reaction time completed, right? That's what enzymes do in your body. Enzymes are essentially chemical catalysts. So this is my reaction with an enzyme. I'm just going to do that one in yellow. Okay, so here's my reaction with the enzyme. And now I'm going to do that same reaction in blue without the enzyme. So here is the reaction without the enzyme. Notice the difference and what is the same. So what's different and what is the same? I'll switch to just a boring color now. We'll go with black. I still start here at the same spot and I still end at the same spot. So that means since my y-axis is energy, my potential energy of the reactants is still the same. My potential energy of the products is still the same. And since my delta H, or the heat of reaction, let's use red for heat, is the difference between the potential energy of the reactants and the potential energy of the products. So I'm going to extend my two flat lines, and my delta H is here. Now let's take a look at the difference between with the enzyme and without the enzyme. So the potential energies have stayed the same. My delta H, my heat of reaction, has stayed the same. So overall, what is different about this reaction without the enzyme and with the enzyme? Let's go to blue. Right, so without the enzyme, I have a much higher hill. With the enzyme, I have a much lower hill. So what gets lowered is the activation energy, the energy to get this reaction started. So without the enzyme, it takes this much energy to get the reaction started, not from the bottom, right? Because you got to start where the reactant line is. So from here to the top of the hill, this is the activation energy with no enzyme present. Now, if I have the enzyme present, let's use a lighter color green. Now it only takes this amount of energy to get the reaction started. So a catalyst is basically a shortcut through the mountain, and shortcuts always make the trip easier. An enzyme is going to make a chemical reaction shorter, less time, less amount of energy needed. So a catalyst is going to shorten the reaction time. The activation energy is lowered. The activation energy is lowered. The activated complex is decreased. Let's go back up to the top. The activated complex, oops, let me go back here. What's a good color for activated complex? Let's go purple. This is the activated complex up at the top here. So this is your activated complex. So I'll just do act complex. And now here is the activated complex, right, which is the reaction intermediate. This is when products start getting formed, right? The reactants break apart. We add some energy to break them apart. Remember, you have to add energy to break a chemical bond. And now we're starting to form the products. So it takes less energy, but everything else stays the same. The only thing that changes are the arrows that have the word activate in it. So another clue that I'm going to give you, which I think I'm going to draw down here at the bottom, is whenever I have this kind of my shape, my graph. So anything, let me just go here. Let me draw that in black. Okay, and then I'll switch back to purple. So anything that's above the line up here, all of these things have the word activate, right? Any arrow or any arrow designated that goes up, that's in the above the curve region, has the word activate in it. And then anything that's under the curve is has the word potential energy. So we have our activation energy, and then now we have potential energy of the reactants, potential energy of the products. If I'm going from here to here, this is my activation energy going in reverse because it's an arrow that falls above the line. And then delta H is always between the two lines, right? Which is potential energy of the products minus the reactants. So knowing all of these lines and knowing the shape of this graph is very important. So now we're just going to keep reviewing this. So the best way to get it better at this graph is just to keep practicing it. So endothermic potential energy diagrams. I know this is endothermic, which means heat is being absorbed, right? Because I end up with a higher potential energy. And your delta H, again, is the difference between the potential energy of your reactants and the potential energy of your product. So how do I know which letter is the delta H? Well, it's whatever arrow fits between those two lines. And then this is the arrow that fits between those two lines. There's your delta H. So we're going to label, which I've already done this, And I am going to switch some colors. So notice I have these words, potential. And now I have these that say activate. And switch colors back to yellow. Remember, and then this is the potential energy of the products minus the potential energy of the reactants. So your delta H, your heat of reaction is letter F, right? So then this is letter F, your delta H in red. Now going back to yellow, anything that has the word potential in it is going to be under the curve. Anything that has the word activate in it is going to be above the curve. So now let's go through and let's label our potentials. The potential energy of the reactants. Reactants is always where you start in a chemical reaction. Products is always where you end. So I'm going to start on the left and I'm going to end on the right because I'm going to read this in the forward direction. So this is my potential energy of my reactants, right? So from the bottom to the reactant line, not to the top of the hill, right? This is the reactant line. This is how much energy is stored in the reactants. So now the potential energy of the products, here's my product line. This is the amount of energy that is stored by the products. So hence why this is labeled letter B. And now the potential energy of the activated complex, right? That's all the way at the top. It has the word activate in it, but it also has the word potential in it. So it has both potential and activate. So that means it's going to go all the way to the top of the curve. And I'm going to use just the color. I'm going to use green for activate, all the way from the bottom, all the way to the top, right? The activated complex is the highest energy state. So that is the potential energy of the activated complex, letter C. So now we're going to do the activation energy of the forward reaction, the activation energy of the reverse reaction. Forward is left to right, and reverse is from right to left. So if I'm reading forward from left to right, the amount of energy to activate the reaction, right? This is where my reaction is going to start. That means this is where I start. This is where I stop. This is the amount of energy, right? So this is the amount of activation energy. And now I'm starting to get too messy on my graph with all my scribbles, so I don't like it. So there we go. This is your activation energy going forward. So now if I'm going to do the reverse reaction, which means I'm going to start here and I'm going to go this way, this is the amount of energy it takes to go in reverse, right? It takes less energy because I've got a smaller hill to climb in the opposite direction. Is this an endothermic or an exothermic graph? Is energy being absorbed or released? Well, I already told you it was endothermic because it's at the top. And my heat of reaction, we already did that. All right, we labeled the activated complex. And now I am going to erase a little bit. Or no, I'm just going to use a different color. We'll go with purple for a catalyst. So if I add a catalyst, is a shortcut. But if I'm making a shortcut and I'm driving from my house to the school and I find a shortcut, I still have to start at my house. I still have to end at the school. I'm just taking an alternate pathway to get there. That's what a catalyst is. It's an alternate pathway that lowers the activation energy. So I still start here. Oops, let me put my line. I still have to start here and I still have to end here, but I just have to make it a shortcut. Well, if I have to go up this big hill to get to school and I want to take a shortcut, maybe there's a tunnel. And then I take this little shortcut. Oh, wait, sorry. Usually we use a dashed line to do a catalyst. Oops. Dashed line to do a catalyst. Ah, look at me with my scribbles. Okay. Let me redo my catalyst line here. And then I got a funny story about my catalyst. Okay, so dash, 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 dash. It doesn't matter how big the hill you make. Doesn't have to be perfect. As long as you start and stop in the same spot, you're fine. Okay, so now let's take a look. What changed, what didn't change? So my activation energy going forward got lower. It only takes this much energy now. My activation energy in reverse is also lower. It only takes like that much energy. But what did not change? The potential energy of the reactants didn't change. The potential energy of the products didn't change because that's the stored energy in the chemical bonds. The delta H also did not change because that's still the difference between these two flat lines. So on the Regents exam many moons ago, when my oldest son took the chemistry Regents, there was a short answer question and it gave a graph and it said, does draw a dashed line to indicate how the graph would look with a catalyst added. So all the students had to do was start and stop in the same spot and just make a little dashed line shortcut. It was the one question my son got wrong on the chemistry Regents, and he did not get 100. Okay, so sometimes it's the easy questions that trip you up. All right, let's take a look at our negative delta H, our exothermic. I know this is exothermic because my product energy line is lower, so then the heat had to go somewhere, so the heat got released. Okay, let me work on my erasing skills. All right, so we're going to start off, and what color was I using for potential? I forgot. Yellow, right? So I have potential energy of the reactants, potential energy of the products, and potential energy of the activated complex. Okay, so potential energies, right, all are under the curve. So here's my potential energy of the reactants, because that's where I start. Here's my potential energy of the products, right? This is how much energy is stored in the bonds in the reactants and the products. The potential energy of the activated complex, well, the activated complex is all the way at the top. So the stored energy, right, potential energy, is all the way from here to here. Now let's look at our activation energy, right? I was using green for activation energy because green means go, start the chemical reaction. So forward reaction. So activation energy forward, that means going this way from left to right, starting with reactants, making the products. How much energy does it take to get up to that hill? This is my potential energy right there, right, or right here. Doesn't matter where you draw the arrow, right? It's the size of the arrow and how it's positioned either above or below the graph. That's important. It doesn't always have to be in the same spot. Now we're going to do the activation energy in the reverse reaction. So that means going this direction. So how much energy does it take to get to the top of the hill? From here to here. So that's E. So remember I said that the arrows could be drawn in any spot. So I can draw that same arrow here, and it's still going to be E. It's still the energy to get from the product line to the top of the hill, the reverse activation energy. The heat of reaction, I like to use red because it just symbolizes heat for me, is the potential energy of the products minus the potential energy of the reactants, right? Where you end minus where you start. So I end here and I start here. So final minus initial. I'm taking a smaller number, right? Because if I had numbers here, this would be a smaller number. Minus a larger number gives me a negative delta H. This is why it's negative, right? Heat is going out. So then I extend my two flat lines, and then the arrow in between those two flat lines is my delta H. I could draw that same arrow here, and this is still going to be delta H because it falls between the two flat lines. The position of the arrow, is not what's important. It's the size of the arrow and how does that arrow fit either below or above the graph. So if a catalyst were added to the above diagram, like which quantities are going to change? All right, so I was using purple for my catalyst. And I'm going to just make this a little bit bigger. So now I am going to just erase some of this red. right here because I want to just change my, there we go. All right. So now I'm going to draw a catalyst and go back to my color. So I still have to start at the same spot and I still have to end at the same spot. But what I need to do is make a shorter reaction pathway, an alternate reaction pathway with a lower activation energy. It takes less energy, everything goes faster. So I have to just make a smaller hill, but I still have to start and stop in the same spots. So I'm just going to make a smaller hill. And then however you do it, if yours was if yours went up higher or lower, it's okay. It doesn't matter, right? We're just showing in general. So now what letters changed? Well, my potential energy of my reactants didn't change because I still start and end at the same spot. My potential energy of the products does not change because I still start and end at the same spot, right? I still have the same amount of stored energy in the reactants and the stored energy in the products. The delta H is the difference between the two flat lines. So my delta H didn't change, right? That still stays the same. But what does change is the activation energy, right? So instead of taking this much energy, it only now takes this much energy. Same thing in reverse. In reverse, it took this much energy to get the reaction going. But now with my catalyst, with my shortcut, my alternate reaction pathway, it takes this much energy to get my maybe a little bit higher, this much energy to get the reaction started. So my activation energy is lowered. And instead of the hill being up here, now my hill is only here. So arrow C gets shortened. So the catalyst, oops, now that's way too big. Okay, my catalyst only changes, so here lowers the hill, doesn't change any of the potential energy. A catalyst only changes things that have the word activate. So either activation energy, forward or reverse, or activated complex. I believe this is your page number 152 in your notes. All right, so let me just shrink. Oops, always doing this. All right, let's just shrink this up a little bit here. All right, so hopefully you got these right. All right, so endothermic or exothermic? Well, I have, I want to start, what color do I want to use? I'll use pink because I haven't used pink. So if I end at a lower energy than where I start, that means the energy had to be released. Okay, so then that's going to be exothermic. I'm just going to throw in a little bit of extra review, negative delta H. The potential energy of the reactant. So remember I said potential energy was yellow and reactants are here where I start. So letter B is the store, anything that has the word potential is under the curve. So that's the potential energy of the reactants. And now this is the amount of energy stored in where I end. So that's the potential energy of the products. The heat of reaction is always the difference between the two flat lines. So I always like to extend my two flat lines, and whatever arrow fits in that space is your delta H. So which is going to be letter D, right? So then it's not always written right here in the center, right? That arrow could be also written right here. Doesn't matter where the arrow is, it's the size of the arrow and how I can shift that arrow and how does it fit under the graph. And number 5, what letter represents the activation energy forward? So remember I was using activation energy for green. Forward is left to right. That's the amount of energy to get the reaction started. So that's right here, A. Oh, this one only takes a little bit of energy. And then the activation energy in reverse is going the opposite direction. So then starting here, this much energy, right? If it takes a little bit of energy going forward, it's going to take more energy to go reverse. And the potential energy of the activated complex, remember anything that has the word potential energy is under the curve. So then that's from the bottom all the way to the top. And that's going to be letter C. So now the reverse reaction, remember reverse is reading that way, endothermic or exothermic. Well, if I'm reading it in reverse, I start low and I end up higher. That's energy getting absorbed, right? Because remember, our y-axis is energy. And then if I add a catalyst, all right, so let's erase all my colors here. And I liked purple for my catalyst. If I add a catalyst, I still start and end at the same spot. And I'm just going to make a little smaller hill. There we go. There's my little smaller hill. What letters change? What shape of the arrow? Well, it looks like C gets smaller, right? So C gets smaller. And then, well, this didn't change, right? That's still going to be between here and here. But A changed. So instead of taking this much energy, now I only need a tiny itty bitty little amount of energy. And then also this arrow changed, right? So I only need this much energy. So only words that have the word activate or active in it are going to change. Because remember, a catalyst is an alternate pathway, right? I made a shortcut and I lower the activation energy of forward and reverse.